Okay, now let's take a look at doing a chi-square analysis where we're going to be looking at using a p-value approach, and we're also going to be looking at applying when we have unequal frequencies in our expected frequencies. So here we're going to be using Benford's law. So we're going to be looking at now, it's a very common problem that's used in terms of identifying fraud. So when we're looking at this, you can see that we're given the data that's the leading digits of the amounts from 784 checks that are issued by 7 suspect companies. If the observed frequencies are subsequently different from the frequencies expected with Benford's law, then the check amounts would appear to result from fraud. And we're being asked to use a significance level of 0.01. So here we have our data here at our bottom that I've pulled up from your text for you. And we're going to go through our first steps here. So again, as with anything, we're going to be starting off, we're looking at our requirements. So here we're looking at doing a simple random sample. We're told to assume that is true. The sample data consists of frequency counts for each of the different categories. So we do have frequency counts for each of them. And for when we're looking at for each category as an expected frequency at least of 5. Now we have 4 zeros here in our data set. Do the 3 zeros below violate this requirement? No, they do not. These are observed frequencies, and the criteria that we're looking at here is set for the expected frequencies. So we do have all of our requirements for proceeding forward. So now we need to identify the specific claim or hypothesis that we're testing. And again, we're looking at the null. So the null would maintain that if Benford's law was true, thus these checks were not a fraud. These were all authentic checks. And I've added Benford's law onto the table for you here. So you can see Benford's law says that 30.1% of them should have a leading digit of 1, 17.6% should have a leading digit of 2, and so forth and so on down the line. So how are we going to convert that to our p-values when we're setting up our null hypotheses? Well, we're going to take our Benford's law and we convert that into the simple formula for probability, which in this case would be 0.301. So we're going to set this up for each of our different digits. So going all the way through, we would add all of these in. So for example, our P of 2 would have a probability of 0.176, right? And so forth down the line until we have all of them. So that's how we set up our null when we're looking at using a particular numerical setup that's pre-existed, such as Benford's law. And again, this would also be what you were using if you were looking at comparing, for example, service usage compared to previous usage of the same services. You would use the ones from the years before as setting up your proportions here, and then you would test accordingly. So my next step is identifying the symbolic form of the original claim as false. And here, again, we don't need to specify which one. We simply need to say that at least one of the proportions is not equal to the given claimed value. And that is sufficient for this problem. So we put these together. Here we have our null, we have our alternative, and now we are ready to move forward for our p-value approach. And the next step we're going to have is what? Well, we need to identify our specified alpha, and so here our alpha is 0.01. And now we're going to determine the p-value with StatsCrunch. So for doing that, we're going to go back into what we were looking at before. So we're going to be setting up the same system, because remember that previous approach gave us our p-value as well. But now we're going to be looking at this in terms of also setting it up when we have expected frequencies that are not equivalent. So here we see, this is the beginning of your StatsCrunch. You should have your observed frequencies entered in just like they have them here. And now I need to figure out what is going to be my expected frequency for each of these. So we're applying Benford's law. We can't assume the expected frequencies are all going to be equal for all 10 categories. That means we can't use the previous formula we used of n divided by k. We are going to use the equation to calculate the unique expected frequency for each digit. So here we're going to be using E equals n times p. Let's take a look at an example of that. So here we can see applying this formula. So I've got 784, that's the number of checks that I have. And for my first option, I times it by 0.301 because that is for Benford's law. and I get a value of 235.984. Notice 3 decimal places out. And that would be my expected frequency for observing a leading digit of a 1. Okay? And then I would go down and do the same thing again, obviously, for option 2 and so forth, all down the line. So pause the video here for a moment and go through and enter those in for your, calculate them and enter them in for your expected values. And then once you have that complete, turn the video back on and let's check the next part together. Okay, so you should have all your data in now, both your observed and your expected, that you've calculated using your N times P formula. And you're going to go through the same steps here, selecting stats, goodness of fit, chi-square, and then loading in your columns. And when you have that completed, hit your calculate. And you should get an output that looks something like this. So here's my chi-square, and again you can see my p-value. You can notice it has my degrees of freedoms provided for me, which is k minus 1. Right? And here we can see our observed and our expected. So we pull out our p-value here. Now our p-value is 0.0001. So when we plug that into making our assessment, we're comparing the p-value to alpha. We're going to set that up as 0.001, is less than or equal to 0.01, and ask ourselves, is this a true statement? Is this true? If it's not, we fail to reject the null. If it is a true statement, then we reject the null. So are we rejecting the null here or not? Yes, we are rejecting the null. 0.0001 is less than 0.01. So we've rejected our null, and we need to restate our decision in the non-technical terms. Here we have our hypotheses again to work with. And so restating this, there is sufficient evidence. Notice again we have our opening statement, sufficient evidence or not sufficient evidence. So in this case there is sufficient evidence to support the claim that the sample is from a population of checks in which the first digits do not occur with the frequency predicted by Benford's law. Okay? So stating back in terms of the claim we've been asked to address, and then coming back to putting it succinctly, thus the check amounts would appear to be due to fraud. So this turns it back then to the overall question that we've been asked to address regarding whether the authenticity of the checks.